All right, happy Monday.
Happy Monday indeed. All right.
We're into week 3. Announcements for the class. If you weren't here, didn't get a chance to hear this from people who were here on Friday, I'm pushing the exam back by a week. The reasoning for that was just that your first assignment isn't due till Wednesday. That gives the TAs under 24 hours to get it back to you so that you can see feedback on that before an exam that would have taken place on Friday. And that's not going to do anybody any good at this point. So I think pushing that back the next week makes a lot of sense, gives you some time to get some feedback, and gives me time to put a little bit more on the exam than just the one topic really that we've covered so far. Asymptotic complexity and recurrence relations I kind of broke under one big bin of analyzing runtimes, and I want to make an exam that's more than just one topic. So you should expect a study guide by this Friday for next Friday's exam. And in the meantime, we're going to cover a bit more material. We're in the middle of probabilistic analysis and probabilistic randomized algorithms. Not too much left of this, just one more problem, I think. And then we're going to dive into balancing binary search trees as a little bit longer unit. This one was very fast. We'll dive into the next one here pretty quickly. Any questions before we get back into our last balls and bins question? Yeah, last time we were in the middle of this question, which was we are going to figure out how many balls have to be tossed on average before each bin contains at least one ball. So we know we have B bins, and if we have B bins, we'll continue tossing. And we decided we were going to use an indicator random variable for this about how many tosses are needed in order for the next empty bin to have a ball in it. If we start with B empty bins, the first throw has to put a ball in a new bin. Then depending on how many bins there are, we use the variable B. The next throw will B minus 1 over B probability to land in a new bin. And otherwise, there's that 1 over B chance that it lands in the bin that the first ball landed in. We continue this process to try to figure out what the expected value of the number of tosses are in order for the next empty bin to have a ball in it. Do we have a chance to think about this expected value? Yeah.
The natural log.
Yeah, ends up being some kind of B times natural log of B of some kind. How do we end up there? What's the reasoning? That ends up being the complexity kind of the whole problem. Let's take a look at potential solution here. So we have B over B minus I plus 1. Take a second to look at that. How does this make sense?
Well, looking at that summation, so it says here in total n is equal to the summation of I equals 1 to B. I'm finding a hard time just trying to find the vocabulary.
Figure out what that means. And let's take a step back from that. N sub I is the number of tosses needed for the ith bin to have a ball in it.
Yeah.
So this is the first bin to have a ball in it, the second bin to have a ball in it, the third bin. So we know that
Yeah, from I minus 1 bin.
it's going to be 1 throw for the first one. It's going to be, how many throws do we need on average? It's going to be very close to 1 for the second one.
Yeah.
Ends up being a geometric distribution. Let's derive. So first we take the expectation of the entirety of the sum. So how many throws is it going to take for each bin to have a ball in it? This is saying that we're summing from I equals 1 to B because every B bin needs to have a ball in it. And each one of those is going to be the number of throws that's needed for the ith bin to have a ball in it. By the time I equals B, then every bin has at least one ball in it, which is the question that we're trying to ask. So we can move that expectation inwards when we recognize that they are independent. It doesn't matter which bin gets a ball in it, it just matters how many are left. So we can move that expectation inwards. And as we do that, we can see that we can just apply the expected value of the ith bin at that point to I as we instantiate I from 1 to B. So we can see now that when we have the sum from I equals 1 to B of B times 1 over I, this is just B times the natural log of B plus some constant that may or may not offset this by a little bit, but doesn't particularly matter in the grand scope of the complexity. So the sum of 1 over I from I equals 1 to B, we saw this before, was the harmonic series. So geometric distribution with probability 1 over B. We change this now to be 1 over I because the concept of B is now changing from I equals 1 to B. So we end up with the sum of the harmonic series, which we showed last time was proportional to the natural log. So we get,
Please continue on.
you're good.
I've worked it out.
B times the log of B basically is the total number of throws needed in order to, on average, say that the B bins will each have at least one ball. So I think the point of this entire unit is to show that the math that you take in your math classes comes back and is relevant to analyzing the kinds of problems that you will see in and around if you need to model something mathematically or come up with an algorithm that doesn't just have a prescribed sequence of steps, but involves some kind of randomization. What can you conclude? How can you use that math to identify how your algorithm is going to behave, and especially how long your algorithm is going to take to run if you want to be able to figure out with this random process, what is the complexity of this as we scale the number of bins, as we scale the number of balls. In this case, we're using some toy example of balls and bins, but you can imagine that this is successes and failures for some real world example. Any questions on how this was derived? Yeah.
I was just curious if, okay, so the harmonic series was also included in the hiring problem.
Yes.
And I'm wondering, like, okay, so now we're seeing it here too, is there like a pattern? I'm trying to see the similarities between the two, it must have something. Like you were saying, success.
Yeah. So when we're trying to figure out how many candidates do we need to interview before we hire the next one, as we see more and more candidates, the sum of the total number that we've seen so far become that denominator that is the harmonic series. And in this case, number of throws before we throw into a bin that we haven't seen before. So it just involves increasing the denominator of the number that we have balls in or hires, people that we've interviewed. When the denominator is increasing by 1 like that, it'll often map somehow to the harmonic series. If we're looking for some kind of success in a 1 over or a B minus 1 over as B is increasing or as the not, yeah. So I think that's the basic idea for how to map a problem we haven't seen before to a harmonic series when the sample, the size of the sample is increasing by 1. Excellent question. Thoughts on that? Thoughts on anything else? Before we dive back to the online hiring problem? Okay.
I might have a question for the problem, I just don't entirely know how to ask them, you know?
Yeah.
So anyway, just please continue, I'll ask it later.
As always, if something comes up in office hours, if you think of something, come ask me in office hours. I frequently take those interactions and incorporate them into the next class as I realize someone had a really good question that deserves some time. So yeah, if you think of something and you can't think of it right in the moment during class, let's talk about it later.
So many of my questions have nothing to do with the concept or just how do you do math?
Practice.
Yeah, I'm pretty experienced in math and I'm just kind of trying to understand it. Like the math logic here and actually, I also been trying to do some proofs on home. I'm a little out of practice, discrete math, but I remember enough about doing mathematical proofs. Well, that has helped a bit too, but, trying to knock myself back in shape.
Fair. You'd like some extra practice problems of things like this, or just in general, a deeper dive into how does this work? This is relying on the geometric distributions formula to come up with the b over b minus I plus 1. If you don't know where to look for that or how to identify what kind of distribution something is to perhaps look at or analyze that, that's something that we should absolutely talk about. Make sure that I get you some help with. All right, one last problem of interest before we dive into a new unit. So the initial hiring problem that we talked about was just hiring the best grader that we've seen so far over and over and over and over again. The online hiring problem says that we can't go through that. Is that how typical hires work out in the real world? You put out an ad and you hire once. You go through an arbitrary number of interviews, but eventually you need to make a decision on who it is that you are hiring, and you do that process once. So we only want to hire once. And the issue with only hiring once is we may not hire the best candidate because according to the online hiring problem, when we interview someone, we have to hire them on the spot or send them loose, deny them on the spot. So you can imagine that there are N candidates for us to interview. How would you optimize algorithmically to hire the best candidate out of that pool that you possibly can? You may see the best candidate on the first interview, but not know that. You may, if you choose to hire the very first person, you'll get an average candidate on average. But if you wait and don't hire that first person, maybe you don't hire the best person because the first person was the best person. So we still need to accept or reject a candidate immediately after their interview. And if you accept someone, now you can't continue to interview additional candidates. You've found the person for the role. So the process terminates as soon as you decide to hire. So let's break into some groups and think about how you would solve this problem. You can instantiate n with whatever you want, 5, 10, 16,400, it doesn't matter. But how algorithmically would you decide when would you stop the interview process? And how would you decide who to hire? Because you can only hire the last person you interview. Question? Yeah.
Is it like an infinite number of interviews you can do?
No, there's a finite number of candidates. We'll call that n. So maybe there are 10 candidates.
But I could interview all of them.
You could interview all of them, but then you would have to hire the last person you interview.
Okay.
So yeah, you hire, if you wait for all 10, then you're hiring the 10th candidate, which is the same as hiring the first candidate. You'll get an average candidate on average, or a random candidate. So how could you improve on hiring a random candidate with some intelligent use of data collection, analysis, and some process moving forward? Because you want to hire a better than average candidate. Now, whatever, you hire the first candidate, you get an average candidate. Hire the last candidate, you get an average candidate. How can you improve on that? Let's talk it through in groups and see what we think, what do we come up with.
Yeah. Yeah. So I'm serious. Actually, that's perfect. I mean, I think I would have thought from the, my thought process is.
You gotta be
Insurance finance knows the average, but also, well. So I'm kind of thinking, so maybe get right, I have to be a right on. Like average, that's why something. Next, we're and. Once you get that average, let's do another course statement, yes. It's actually another average, so don't worry about people. And just, find the person who's like above that average. Because.
Interesting. Okay, that should, on average, net you a better than average candidate.
Yeah.
But I would argue it does not optimize the problem.
Oh, for sure, yeah.
So that's a very good start.
Well, first, yeah, first, let's figure out. What sets of variables that's sense. Looking at it, but you know, with them that. That's just like. Or those that. If they have standards. Then you know, their shifted itself or higher than otherwise.
That's what.
Do the next one.
Yeah, it was a good place. So we never hired him.
I'm the oldest.
So. Very hard to say. I'll do that.
Yeah, well, it's something else. Thinking. We're missing a bit about Johnny and Bob's hospital, I'm building up those albums, so that's good.
I don't know.
Yeah, we said hire people just on the spot.
This is good cases to build in search clarity, but it's enough. That's true.
What thoughts do we have, just from an initial thinking about the problem? How could you hire, we had one instance during this of discussing some algorithm that would get you better than an average candidate? Any other thoughts on just something you can do, does not need to be optimal, something you could do to hire a better than average candidate? Yeah.
Well, the thing about this is like, well, what exactly is, a part of it is just like, what exactly is it that you're looking for? I think the first thing I would do would be just, write down some specific variable standards saying, this is exactly what I'm looking for, then and then there, you know, we be interviewing the candidates one at a time. If they meet that threshold, we hire them immediately, and if not, we, just, you know, stop the interviewing and then after, and if not, we continue interviewing. Get where I'm going.
Yeah, that's a very real world type of how a real world interview is done. Imagining that the candidates that we get are going to have numbers associated with them between 1 and 10. But when we interview them, we just know whether they've been better or worse than the existing candidates that we've seen so far. So
Yeah.
imagine putting 1 through 10 in an array, randomly permuting it,
Mhm.
and then kind of from what you've seen so far, you could rank the candidates that we've seen so far. So I interviewed
Yeah.
3 candidates, and I could see that candidate 2 was better than candidate 1, who was better than candidate 3. What does that tell us about whether we should interview a 4th candidate or accept candidate 3?
Okay. Your point?
So we don't, there's no way to come up with there's no way to know in advance that you have. One for each.
You know N, so you know I have up to 10 people to interview. But yeah, given that you've interviewed 3 people, you don't know whether you've interviewed, if we're looking from 1 through 10, 1, 2, and 3, or 2, 8, and 9, or 8, 9, and 10, or you just know that I've seen 3 candidates and I can rank those 3 candidates from best to worst that I've seen so far.
Is this like if everybody has like the same resume, so you can't even look?
Yeah, it's just a matter of, do you interview the next person based on how many people you've seen so far and their relative rankings with respect to each other? Yeah,
You establish a threshold to saying, okay, a 7 and above is good enough.
if you knew what a 7 was at that point, or when you'd seen the 7, you just know I've seen 3 candidates and I can rank them 1, 2, and 3. Underneath the hood, you know that you've seen some subset of the numbers 1 through 10, but you don't know that's hidden from. The right process, if you could see the numbers, is wait until the candidate with skill 10 shows up and hire them. But you wouldn't know that. You could have seen that person as the very first person you saw, establishing the baseline. If you ever interview someone past the first candidate and the best candidate was that first candidate, you'll never hire the best candidate.
You never know, you don't know that skill 10 is the best. Or do you know?
You would know that of these 10 people, there is a best hire. So basically, we're just ranking them from 1 to 10. By the time you interviewed all 10, you would know that ranking. But as you're interviewing, you only know the relative ranking of those you've seen already. Yeah.
So an idea that I had, is you're gonna rate and reject your first candidate. And then you're going to try to find someone who's just better than that first one. I think there's a good probability there that you're gonna get an above average candidate.
That's a very good way of thinking of the problem. If we could scale that a little bit, we could say, let's interview the first I candidates. And you could look at either the average of the first I candidates, the best of the first I candidates, something from those first I candidates as you switch from the data gathering phase of I'm going to just start interviewing people and rejecting them as I figure out what does an average worker look like. The larger sample you have, the better understanding you have of where that average is. When the law of large numbers kicks in a little bit more and a little bit more. And then from there, you go from data gathering to optimizing, where given that you have n minus I candidates remaining, how could you utilize how many people are left to try to optimize of those people? How can I hire the best of who's left? Other thoughts or ideas? Yeah.
Been really so long. Well, you report out rates. But maybe what I was thinking, maybe randomly selecting people, checking how they scored. I think we say pack a little much, maybe something like that. And
Yeah.
when I mean by the quartile range, like how you kind of like identify outliers from the like average. I think from that, if it's like above that range, on like iterating randomly from that average. Kind of like what I said earlier. Statistics actually.
Yeah.
The average.
Yeah. I actually really like this as just a problem to give people to try to go optimize. So the way that you might do this is you're all going to come up with a different algorithm as a way of optimizing this process. Just get a very large sample of this. Run this a million times. You're going to take an array from 1 to 10, randomly commute it with some sorting algorithm, then apply your algorithm to that sort. And see if, given the algorithm that you select, what is the average quality of candidate that you do hire? And then we could compare, given the algorithms that people implement, who creates the one that has the best hiring procedure. That would be a very fun assignment that I unfortunately am thinking of right now instead of a while ago.
Okay.
But let's take a look at one approach. Is there something else to add to that?
Well, I was just curious about the quartile because we're saying that each candidate has a 1/n probability of being the best candidate.
Yes.
So I don't know, it's just like we have to assume that each of these candidates.
That is true.
Yeah.
The question is, how could we optimize the average candidate that we hire? It would be one thing to try to optimize the chance that we hire the single best candidate. But that's gonna be a slightly different question than optimize the quality of the candidate that we hire. Yeah,
Is N gonna be a known value?
yes. You know how many candidates are in the pool. So let's take a look at a potential approach. So we've interviewed K candidates, and we're going to rank every one that we've seen so far. So after we've seen K candidates, we have a ranking from 1 to K of those candidates. After we've seen K candidates, stop collecting this data and hire the first candidate we see who is better than each of the first K candidates. What do we think about this process? Analyze this from kind of a what happens perspective. What happens and how likely is that outcome? Yeah,
So the probability of firing, like interviewing and then not accepting them, be like A over I. That would be like the first, if the best person is the set that we're automatically firing.
yeah. Then we would hire the last candidate and get an average candidate on average. If within the first K candidates, we have the best candidate. That doesn't seem great, but at the same time, if we haven't seen the first candidate, the best candidate yet, through the first K candidates, we know we are hiring someone who is better than the entirety of the first K that we've seen so far. That could be the maximum, but it could be that if it's 1 through 10 and the best candidate in the first K is 8, now the question is, does 9 come before 10 or 10 come before 9? But regardless, we're hiring one of the 2 best candidates if the best is the 8 out of the first K candidates. So we either hit or we miss horribly. But the miss horribly still ends up being an average worker on average. So I'm not going to assert that this is the single best algorithm to solve this, but it gives us a baseline to try to optimize from. If we made this assumption that this is the process we are going to take, then we could try to optimize and say, what is the best value of K? How many candidates should we interview? And what should we do? How likely are we to optimize the problem if we have a K of 1 or a K of n minus 1 or anything in between that? So 2 outcomes. If the best candidate was within the first candidate, then we hire the very last candidate, which will be an average quality candidate. And so we should try to figure out what is the optimal value of K, so that when we run this procedure a million times, on average, we hire the best candidate that we can. So given that, let's in groups try to figure out how could we determine the best value for K? How many people should we interview before we switch from data collection to figuring out who to hire? It's fairly intuitively apparent that the extreme values of K are bad.
Yeah.
K equals 1, not optimal. K equals n minus 1, not optimal.
Yeah.
Really?
I'm sure from you. I said, yeah, God, truly. But I feel like there's more I want that first part was good. You know, okay, so I don't. Yeah, I don't know if I'm right. But it's more to it. I think 1 hour, like everything, there's long for 1 hour and. This audible volume, actually, well. The best thing. It's not to you.
Yeah,
This might be cheating, but I think I've seen this problem before. I mean, isn't it 1 over E %? That's that you can come.
you've seen it before.
Yeah.
I don't think you're really wrong on that one.
That is
actually-
exactly right.
This is actually, yeah, before you continue, this is actually very familiar when I think about it. Seen a familiar problem like this, but please continue.
Yeah. Good. Yeah,
Kind of overheard, over.
1/3, yeah. It's, so since there are n candidates, if we multiply n by 1/e, that proportion is the appropriate value. Let's actually go through it and see why. So the way that I like to envision why or how this scales is to start with a small but not trivial problem. So if we set n equal to 3, if we accept the first candidate that we hire, we have a 1 in 3 chance to hire the best candidate, if we just hire the first candidate. If we reject the first, whatever value that happens to be, then hire the next candidate better than them, how likely are we to have hired the best candidate? So 1/3 of the time, there's no way to hire the best candidate. But 2/3 of the time, we're going to take the average of that. So break it down a bit. Let's actually draw this out. So if there's a 1 in the first position, then we're either hiring a 2 or a 3, equally likely. So on average, if there's a 1 in the first position, we hire a candidate with value 2.5. If there's a 2 in the first position, then we know we're hiring the 3. It doesn't matter if what comes next is 1-3 or 3-1. The next candidate who's better than this 2 is the best candidate. So you're hiring an average of 3 in that case. And if 3 is the first number that appears, then you're not going to hire until the last hire, which is equally likely to be a 2 or a 1. So you'd hire an average of a candidate with value 1.5. Since these are all equally likely, you just take the average. 7/3 is what we're going to get on average. The average candidate in this case would be a 2, so we've improved on the average in this case. Make sense how and why I got there?
Let's see. We have 4, then at 3. Yeah, the math adds up.
So how likely are we to have hired the best candidate? In this case, we hired the best candidate. In this case, we hired the best candidate. In no other case, we hired the best candidate. There are 6 possible permutations, and we hired the best candidate 3 out of 6 times. 50% of the time, we got a 1 in 3. That feels like an improvement over at least selecting randomly.
Yeah.
Does that make sense?
Yeah, I think it does so far.
There are 6 possible permutations as to the ordering of the candidates. And we hired the best candidate in both of these and in one of those. So 3 times we hired the best candidate out of 6 possibilities. The average candidate is better than the average candidate in the pool. The average candidate that we hire. So you can start to use induction at this point and say, if we've figured out this problem for size 3, how does this change for size 4? So if n is 4, is it better to stop collecting after the first candidate or the second candidate? We can start to agree that stopping to collect data after the third candidate is a bad idea. But is it better for the first or the second? So we can start to draw that out. So we either see what comes first is 1, and if we're collecting data, if we're stopping after the first, then we're going to get an average of the next best candidate is going to be this position. It's equally likely to be a 2, a 3, or a 4. So on average, here we're hiring a candidate with quality 3 between 1 and 4. If we get a 2, then we're gonna ignore a 1 if it shows up next. Where the question is just, does the 3 or the 4 show up next? So that gives us an average between a 3 and a 4, which is a 3.5. If the first candidate we see is a 3, then we know we're gonna take the 4, so that average is a 4. The only one better than this is a 4. And if we see a 4, we're going to take the average of 1, 2, and 3 because we're going to wait until the very end. So when there are 3 open positions here, there are an equal of the same 6 permutations that we just had before. So this average is going to be an average of a 2. Each of these is equally likely based on just which is going to come first. So we would take the straight average of that. 12.5 over 4 is just over 3. Three point something. Doesn't matter a ton, but it's better than the average of 2.5. The average of 1 and 2 and 3 and 4, 2.5. But we've improved on that. The question is it better to have done that and collected data on n equals 2? So how would we answer the n equals 2 problem? We now have to look at every possible combination of what could come in the first and second position. So we would have a 1, 2, 1, 3, 1, 4. That's everything for a 1, 2, 1, 2, 3, 2, 4, 3, 1, 3, 2, 3, 4. Running out of room. 4, 1, 4, 2, 4, 3. So we're looking to improve on the best of everything that we've seen so far, and we collect data on the first 2 candidates. So if we collect on 1 and 2, then we're going to accept the first candidate that's better than 1 or 2, which is going to be either 3 or 4 equally likely. So this gives us 3.5. Down here, we see 1 and 3. We're getting 4 for sure because we're waiting for the first candidate that's better than that. If we see 1 and 4, we're equally likely. Between 2 and 3, we're going to take the last candidate regardless. That's 2.5. Between 2 and 1, that's the exact same thing as 1 and 2. Should have moved this over a little bit more. That gives us the same 3.5 because we haven't seen if this place is either 3 or 4. Take the average of those since they're equally likely to be the next one that shows up. Gives us 3.5. Between 2 and 3, we're going to hire the best that's better than that, guarantees us 4. Between 2 and 4, there's no one better than that. So we're going to hire the last candidate that's either a 1 or a 3, gives us an average of a 2. 3 and 1, always going to get the 4. 3 and 2, always going to get the 4. 3 and 4, we're going to get the average of the 1 and the 2. That's unfortunate. We get an average of 1.5. 4 and 1, take the last one. Between 2 and 3, average is 2.5. 4 and 2, we're either going to get the 1 or the 3, average is a 2. 4 and 3, between 1 and 2, that's 1.5. And again, these are all equally likely. So we take the average. How much mental math do I want to do?
That is a lot of math indeed.
7, 9, 10, 13, 17, 19, 23, 27, 28, 29, 31, 33, 34, 35 over 3, 6, 9, 12, 39 over 12, which is 123.25.
Yeah, that's about right. Oh, and the answer for the first one was 3.125, which was 12.5 divided by 4.
Yeah,
So
the 3.125.
just trying to help you.
Yeah, that's great. So it looks like collecting data for 2 was ever so slightly than collecting data for 1. And it turns out the reason that was is it's closer to that 1 over e value, which gives us about 38%. But this is one way that you might choose to see the problem and break it out. You can solve this theoretically, mathematically, but you can also break this down logically and start to think about, well, which one of these is better? What is the overarching problem? How do we work through that? Any questions on the logic or work that I've drawn out?
I believe that 39 is supposed to be 5.
Is it, did I say, is this 35?
Yeah,
That's a problem. This makes it worse.
Gives you 2.91.
oh, yeah, 2.91, then 6. Eating, and I'm not gonna go into that.
So in this case, we've collected too much data. And we see that this should be something that starts low, gets high, and then goes low again. So there should be an optimal point where we hire the best candidate. And it should be in between 1 and 2 somewhere. But as we make a larger and larger N here, we're going to be able to divide this down into and see where that peak appears on average as we get more and more information. So it ends up converging to 1/8, about 37% is the appropriate amount of data to gather. So if we're taking this general approach, what we should do is collect data for 37%, regardless of who it is, how talented they are with proportion to the rest of the candidate pool. Automatically reject the first 37% and then hire the next candidate who's better than the first 37%. And there is a whole proof for this in the book as to why that is, but it's very interesting. What are some other interesting applications of this idea? Anyone think, what is another example of the online hiring problem in terms of a real world application?
Wait till after the first 30 seconds. Application.
Yeah. So look at and go through 37% of your in-person interviews that you get, and then throughout your resume, continue to interview and then accept the next best offer. Better than the first 37% of all possibilities. Of course, that would require you to know exactly how many jobs are out there, how many jobs you're going to get an interview for in advance. So not quite as useful as we would like it to be, but it gives us kind of an interesting baseline of if we're trying to get one job for the rest of our lives, that would be a reasonable approach. The one that I've come prepared with is potential partners in life. If you want to get married exactly once, go through about 37% of your potential partners in life, and then marry the next person you meet who is better than everyone you've dated before. It's a strange application a little bit, but the more you think about it, it starts to make a little bit more sense, I guess.
The average.
That's a good question. Didn't come prepared. So in general, when you see something like this, where you have to make a permanent decision, it's worthwhile to explore the options that are available to you before making an important decision, like hiring someone, deciding to get married. Plenty of other applications out there, but you can apply this same kind of mathematical principle to just about any important decision that you make. That it's worthwhile to gather some data, and then with that data, you can start to figure out and analyze what is actually good, as opposed to just what is good based on what I've seen so far. There's a threshold of experience that you need to get in order to be able to answer the question, what is good? And you optimize if you gather data about 37% of the possibilities before you make that decision. Interesting result. Any questions on that?
What does N represent in terms of potential partner?
You can imagine that if you're going to set a deadline, something that says like, all right, if I'm not married by when I am X years old, then there's something I want to be married by the time I am this old. You can imagine going on dates and until you are that old. N is the number of people you would go on dates with, and that would be the sample size of if I spend this much of my time looking for the optimal partner, then that's the maximum amount of data that you could gather before you would have needed to have made a decision. But it's not necessarily possible to go back to the very first person you went on a date with and expect that they're still interested in marrying you if it's been 25 years since that date. That's a really awkward conversation waiting to happen. Of course, we'd have to guess at that. No one really knows. If I wait until I'm 45 to get married, how many people will I have gone on dates with trying to find the optimal person to marry? That's a challenging question. You don't know what that N is at any point, but you can guess and use that to make an informed decision. Who knows?
Or if you're on.
Take from this what you will. What was that? Sorry?
It's helpful if you're on The Bachelor.
Yeah, right. You do know what the N is on The Bachelor. If only they would go through this would be a fun Bachelor worth watching to me. A mathematical analysis of the decisions that you're making. Strip the emotion out of it completely. All right, I'm going to rate people, and then after I've collected enough data and booted enough people off the show, then I'm going to figure it out.
I just want to make sure you said rate.
Yes.
T.
Yes, very important distinction.
Just want to make sure.
If I'm not enunciating that well enough, let me know. It's a very important distinction. Okay. With just a few minutes, I can introduce this idea before.
I thought there was the start from beginning, but whatever.
There it is. Okay, switching topics completely. How much do we remember from binary search trees from data structures? Maybe a show of thumbs. I could open my computer and make one from scratch right now. I know how they work, but I would need a little bit of experience. Preparation.
More practice resharpening it for me, but I remember
Yeah.
a lot.
So it looks like we could use some refreshers on binary search trees. That is a good question. Where is this in the balance? So in the textbook, they're going to go over red-black trees, and I am not going to go over red-black trees beyond at an overview level. I'm going to use a different balancing technique. So the book won't be quite as helpful for what I'm going to go over, but I will talk about the differences between the algorithm the book describes and the algorithm that I'm going to go over. One of them is easier to understand, a little bit harder to implement. One of them is harder to understand and a little bit easier to implement, and they optimize for different things. So, binary search trees. If you haven't seen one in a while, here's a binary search tree. What do we notice about what this is? How can we describe this structure? What is it doing? How do we make sense of where the numbers are with proportion to each or with relation to each other?
All numbers on the left.
Yeah,
Smaller on the left, larger on the right.
pretty much. Yeah, that's about right.
And we could just define that recursively. Given the root node is 10,
Yes.
everything less than 10 is to its left, everything larger than it is to its right. If you recurse on its left child, which is 8, everything less than 8 is on its left, everything greater than 8 is on its right. So, binary search trees. Every node has exactly 2 children. Those children may be null, but there are always exactly 2 children. We cannot have more than 2 children, and we cannot have less than 2 children. Again, there may be null values in that exactly 2. And given that we have a node with a value, every node in the left subtree is less than that node's value, and every node in the right subtree is a value greater than that node. And that is true, again, recursively for every node in the tree. Who can recall how we print nodes in order? What procedure goes through and prints in this case? 1, 2, 3, 4, 5, 6, 8, 10, 11, 13, 14, 16. Yeah,
In order traversal.
some kind of in-order traversal.
Yes.
What do we use for in-order traversal? How did that work?
Basically goes left, center, right. That's how they usually do it, from what I remember.
Yeah, left node, right. And L and R traversal. So if we use L and R, we can, something's happening up there.
What the?
I always love how the projector is attached to the ceilings. When anyone walks by, that bounces, so this bounces.
I don't know, thought an earthquake would be happening, which is a lot more terrifying when I see that out loud.
So we start with 10. Before we print the 10, which is the end step, we're going to go through every one of these nodes has basically the equivalent of an LNR on it. So 10 left means to call the left node before the end process is to print what's on the value of the node. So go L. From this perspective, we haven't started yet, so we're going to go L. From this node's perspective, we haven't started yet, so we're going to go L. From this node's perspective, we haven't started yet, so we're going to go L to this null child. We're going to go through the entire LNR procedure at that null child, because there's nothing to print. Once we're done with that, we move back here. When we're here, we've now done the L step. So what's left is N and R. The N is going to print the value of the node. We're done with the N, so we're going to go to the R process. Again, there's a null left, null right child. So we're done with that. We're done with this entire node. So we can move back. From this perspective, we've done the L. So we need to print the node, which is a 2. Before we move right, we'll go down the right subtree. We haven't started this yet, so we're going to go through the entire LNR procedure, starting with left. Then left. Left node right, if it's null child, back to here where we print the node. Right, that has nothing. We're done with this node, so we move back, print this node. Move right. We go through the LNR, LN, prints the 5. Nothing in the right, that one's done. Come back. This is completely done now, so we move back to here. And we've done the left subtree, so we print the node. We go to the right. We backtrack, we backtrack. We've now done everything here. We come back here. We've done the entire left, so we print the node. We go right, there's nothing. We come back. We've done the left, so we print the node. We go down the left, nothing here, so we come back and print the node. We go down the right. I guess we've done the L and the R here.
Yeah.
So we go to here, left, come back, print, 13, back, come back, print, back, left, come back, print. And then we just move backwards through everything to the very end and call it a day. But what we printed was the nodes that are in order. And we'll come back to this tomorrow.
Wow.
And figure out how we can balance this tree, because it's great to have a tree structure as long as it stays in a relatively balanced state. So we'll look at why that's important and what we can do about it tomorrow. Office hours starting now for anyone who wants help with anything. I'll be there for the next couple hours.
All right. One move it to